you who don't know me. And this is Deep Robotic Learning. It has all the buzzwords. Ooh. So maybe we'll start with some logistics, and then I'll talk about some philosophy, and then we'll look at a few papers. And today is going to be light on math. It's just introduction of what we're going to talk about this quarter, and maybe we'll get to know each other a little bit. Can you all hear me? Good. Right, so maybe we'll start with some logistics. Well, we meet here on Mondays and Wednesdays from 1:30 to 2:50, 3, whatever. And I'm the instructor, and Kay is our TA. And we'll have office hours on Fridays from 4 to 5 for me, and Mondays 3 to 4 for Kay. If you need to reach me, email me, or anytime my door's open, just walk in. It's fine. Yeah, so we're here to help you. If you have any questions, email me or use EdSTEM. Either of those things work. And if you have enrollment questions or anything like that, just stay back after the class and we'll figure it out. Right, so the way the class is going to work is that we're going to have 50% of our grade on the final project. So it's pretty heavy on the project. We'll have 6 discussion sections where we're going to discuss papers and present them. And I'll talk about that in a sec. So that's 20% of your grade. 15% of your grade is on some readings and leaving a few comments on them. And then 15% of your grade is on doing 2 assigned homeworks. They're in Python plus PyTorch. They're super easy. So easy. And overall, grading is not that serious. It'll be fine. I just want you guys to show up and participate, and that's basically it. Most of our communication will be through EdSTEM. I don't know if has everyone signed up for EdSTEM or seen it? Yes? No? If not, talk to me after the class and we'll figure out the logistics. But that's an easy way for you to post questions, to form project groups, to leave. That's how we're going to do discussion, section organization, leaving comments on paper readings, and so on. And if you have any personal questions you don't want to broadcast, just email me. Okay, so generally what we're going to do is we're going to have one lecture by me, or we have a few guest lecturers. Kay is going to give a lecture, and then we're going to have these discussion sections where you're going to present a couple of papers, and we'll talk about that in a second. But the format is seminar style, so the hope is that it's very discussion based. It's not just me monologuing, like interrupt me, please participate. Otherwise, I'll start calling you out. It's not great. Right? So please do participate. Interrupt me whenever. We want to go slow. We want to discuss it. And then at the end of the class, we're going to have some final projects, which we're going to present in a poster session. Hopefully, we'll have some cool demos. Hopefully, people from outside of the class will come and see your posters, and it'll be fun. And in between, we want to have some project proposals and milestone check-ins, which I'll talk about in a second. Make sense? Cool. Yeah, please participate. So do interrupt me. Okay, so regarding the final project, there's 3 parts to it: the proposal, a milestone report halfway, and then a final report. And really, anything related to deep robotic learning is fine. Right? So anything related to learning and robotics is good. It can be a new algorithm, a new implementation, something that's performant, faster, more stable. An empirical investigation into some class of methods, either on a robot or in simulation is fine. A new robotics application is great, etc. And I'll let you guys choose what you want, but let's have something related to robotics and something related to learning, and then we're good. Right? I'll post a set of ideas to help seed some of these projects, but you can do them in groups of 1 or 2 students. We don't expect them to be at the level of a publication, just something that's fun and interesting to look at. And those of you who are doing research, just reuse your research. Don't do double the work. Right? So that'll fit it in, and it'll work out. And if you have questions about whether your projects work or not, just come talk to me. Okay. Right. So Kay and I discussed this new format for our discussion sections, which I'll run by you. Let me know what you think. So we're trying this many-to-many role-playing format, which some folks at UNC and Toronto are looking at. And the idea is that when we do paper presentations, usually one person is just talking and everyone else just sits and half of you fall asleep and it just sucks, right? So instead, what we're going to have is we're going to have for every paper, rather than one person presenting, we're going to have many different roles, right? And so every paper has 6 or 7 people participating, and then it's much more of a discussion, and each person fulfills a different role, right? So the roles we're going to consider are, we're going to have one person who's the discussion leader, right? So they're going to give you an overview of the paper, basically what the method is, what the basic results are, just kind of contextualize the paper, right? And kind of make sure everyone else is ready to present. Then you're going to have a paper reviewer 1 who presents the pros of the paper, right? So reviewer 1 who is trying to argue why the paper should be accepted, right? So you're trying to like figure out act as if you're a paper reviewer and give comments on why you should accept this paper strongly. Right? Paper reviewer 2 who's going to argue why we shouldn't accept the paper, right? So we're going to argue for flaws in the paper, methodologically, empirically, related work, whatever, right? You're going to argue why this paper is not good. You're going to have an archaeologist who identifies where the paper lies in the stack of related work, right? So contextualizes it in the body of literature. We're going to have an academic researcher who says, okay, this paper is done, let's try to build the next paper. So it's going to propose follow-up ideas on this paper. And lastly, we're going to have an industry practitioner who's going to look at the results of this paper. It could be a theory or empirical paper, and then try to propose applications that can follow from this, and what are the impact societally and practically of these applications. And so the hope is that every paper has all of these roles. So I think there's 6 roles, right? So every paper has all of these roles participating, and so each person gets maybe 5 or 6 minutes to present, and so all of us participate a lot more, right? I'll post a link of like more details of this, but this is the general format that I'm thinking. It's a little new. There's going to be some kinks, but maybe let's try it out, right? What do you guys think? Yes? It'll be different. Okay, and then for the weeks that we do discussions, I posted on the schedule which weeks we're going to do discussions. Only the people who are presenting will present. There's no need to leave paper commentaries on those weeks. On the other weeks where I'm lecturing, or Kay's lecturing, we'll put some readings up. The readings are relevant to the stuff, but like go beyond the class material. I think everyone should read at least one of the papers presented or like proposed, right? And then post some commentary on it. So don't just copy the paper abstract. Just like post something that you found interesting in the paper, something you found problematic in the paper, something you want to follow up on, a question you had, right? And you post it on Edstein. We'll start a thread for every week and just post which of the papers you read. You can read all the papers if you want, but at least read one and leave a comment, and you'll get some grade on whether you leave a comment or not. And the papers are, we're not going to post 70-page theory papers. They'll be manageable, right? So for discussion sections, you don't have to leave comments. For every other thing, try to leave a comment. You're also welcome to leave comments on discussion papers. You just don't have to. Does that make sense as a format? Okay. Okay, so who am I? I am 3 months old at UW, so I'm a brand new assistant professor here. I grew up in Oregon and India, and I spent 10 years in Berkeley, so I'm largely Berkeleyan. So I did my undergrad and PhD at Berkeley. I was at MIT last year for a postdoc, and now I'm here. And I'm super excited to be here. This is my first class teaching. And yeah, it's really a privilege to teach all of you. So, yeah. Things I'm interested in is reinforcement learning, robotics, optimization, robustness, machine learning generally, generalization, lots of things. So if you're interested in any of those things, you want to do research with me, come talk to me afterwards. We can figure that out. Sometimes outside of work, I like to do other things. I like to play tennis and soccer, draw sometimes. We're gonna adopt a dog soon, so that's exciting. Yeah, so that's me. And I'll let Kay introduce herself.
Hey, I'm Kay. I have been here in the last 5 years as a PhD student, so this is my 6th year. I've been here for a while. I'm interested in applied robotic learning, and I built a chopsticks robot as a test bed.
Awesome. Okay, so let's maybe I'll tell you guys a little bit about what this course is about, some history on RL, and introduce a bit of notation, right? Okay, so what is this course about? I want to build robots that get better over time and are able to adapt to new environments, right? So if you have your Roomba, you put it in a new home. I want it to get better the longer it spends in your home, right? So if you had a Roomba, you see it gets stuck all the time. It doesn't really get better, but we want to build robots that get better adapting to new environments. We want to build robots that get better adapting to new objects, right? So if you have a robot that is grasping, you want it to, let's say, let's say you have a new object that you give it. You want it to get better at grasping that object consistently in new scenarios, right? So you want it to be able to adapt to new objects. You want robots that can adapt to new terrain. Okay, so this is a video. Oh, just before we get there, this is a video from Google Brain showing their grasping system, Qt Opt. And it's pretty good at grasping a variety of different objects, doing different tasks. And so they have 14 of these arms, which learn all the time and get better as they get more experience. And then we want robots that get better over time, adapting to new terrains, right? So if you have quadruped robots, you want to, throw them on a new hiking trail, and you want them to get better over time, right? So you want to be able to deploy robots into the wild. Maybe they're not perfect as they hike, but they get better as they spend more and more time in your environment. So you want them to be able to adapt to new terrains. And so this is some really cool work from Marco Hutter at ETH. And Byron's group does some really awesome work on this project. And then you want robots that get better at new tasks, right? So let's say you have this robot hand that you want to do in-hand reorientation, right? You want it to spend a bunch of time practicing this task autonomously, and then figuring out how to do it with experience. No. It's fine. Basically, as it spends longer and longer in the environment, you want it to practice and get better and better, eventually learning how to do fairly complicated tasks, right? So you want it to continue having more and more experience in the environment. So you want to be able to very quickly teach it new tasks rather than have to sit and hand code every single behavior, right? So you want, basically the goal is to build adaptive robots, right? And the way we're going to do it is using a combination of embodied systems and machine learning, right? So what do I mean by an embodied system? It's any system that can sense, plan, act, right? So you want a system that can sense the environment through some set of sensors, cameras, LiDAR, touch sensors, whatever, and then act through some set of actuators, right? So these are some robots. You can extend this to control engineering, you can extend this to other stuff, but we want to consider any embodied systems in the physical world. And then you want to combine it with machine learning algorithms. And when I say machine learning algorithms, I mean any algorithms that can accept data and get better using that data in order to learn things, right? And so we want to combine embodied systems with machine learning algorithms to get these adaptive robotic systems, right? And so the question we should ask is, how exactly should we do this combination of embodied systems and learning algorithms? Do you have a question? Yeah.
Yeah, so I have one question. So what's the difference between an embodied system and robotics? What's these two terms are different?
Yeah, that's a good question. I guess I was thinking when we say embodied system, it's okay to have like a chemical plant or like any other thing in the physical world, for instance. It doesn't have to be, or like a conveyor belt or like an autonomous car. Whereas usually robots, when you think of robots, are just these kinds of robot arms and like more humanoid or those kinds of robots. I think the ideas we're going to introduce in the class can be extended to arbitrarily complex physical systems that are making decisions in the world.
Okay, so it's like robotics, kind of like subset.
It's a subset of robotics. Yeah. Cool. Right. So yeah, we want to combine these two. So the question we want to ask is it just a matter of, pineapple penning the situation, right? Do we just take our best embodied systems and do we just take our best learning algorithms and slap them together and are we done, right? And obviously the answer is no, because why would we have a class otherwise? And the answer is no, because the problem of combining embodied systems with learning algorithms is more difficult for lots of reasons, which we'll get into. But some examples are most learning algorithms do prediction. Here we want to do sequential decision making, which is a slightly different problem. In robotics, data efficiency matters, right? Because data is not free. And so compared to like language models, we need to think more carefully about data. Because you're having algorithms that collect their own data, exploration matters, safety matters because you can't kill everyone in the process of learning, and so on, right? So there's going to be a bunch of things that make this not just a pineapple pen, and so we want to think carefully about how we combine these embodied systems with these learning algorithms, right? Okay, so let's think about why we should care about robotics in the first place, right? So there's the obvious reasons that there's a lot of downstream applications, right? So here's some that I think are compelling. So there's agriculture, there's warehouse robotics, industrial packing, autonomous driving, surgery, home robotics, assisted feeding. Those are some that I think are impactful. Do other people have things they care about, which we haven't listed?
Solving scientific
problems. Yeah. So doing experimentation and solving scientific problems.
Is cooking robot is like home robot too?
I guess, yeah. I was thinking that comes under home robotics. Yeah.
I think when I moved on robotics, I feel like I've seen like animal as robots for like more support and for like comfort people.
Yeah. I guess assistive, comfort, social robots. Yeah, for sure.
Robots in space.
Robots in space. Yeah, that's super useful. Great.
Robots for like rescuing people.
Right. Search and rescue. Totally forgot search and rescue. That's great. Delivery. Right. So there's downstream applications. Yeah, we should care about them. But I think that maybe the reasons for caring about robotics might be a little deeper than just applications, right? So there's this interesting experiment that these two researchers at Brandeis University did in the 60s. Right. So it's this like kitten experiment. Do people know about this? Yes. Okay. So the idea here is that they want to argue that intelligence depends on embodiment or the ability to take actions in the environment, perform experiments, right? And so what they did is, it's a little bit cruel maybe, but they had these two kittens, right? They put them on a carousel, and one of the kittens is an active kitten, so they can interact with the world, they can take steps and move around. The other kitten is able to, receive all the input that is coming from the first kitten, but is not able to affect the world with its actions, right? So it's able to receive sensory input, its feet can actually touch the ground, but it's put in this basket, so it's like not able to actually move the carousel in any other way, right? So it's just receiving passive input. And then they try to study when you like have these two kittens that are blind until the point where this is happening, what happens to their intelligent development, right? So they run a bunch of these tests to see, okay, how good is your paw placement? How good is your cliff avoidance? How good are you able to deal with new objects, tactile response, and so on, right? And so the argument is that basically they want to show that there's a difference between the active kitten and the passive kitten in terms of the learned behavior, right? And so some somewhat striking results are that they considered this visual cliff experiment, which is saying that the kitten is on a cliff, one side is shallow, one side is deep, and they want to see which way the kitten steps, right? Because the deep cliff will be unsafe and the shallow cliff is safe. And they find that the active kitten almost always or exactly always goes to the shallow side and is safe, but the passive kitten basically chooses almost at random, right? And they have a similar set of results for all the other criteria as well, which suggests that perhaps there's something more to the idea that intelligence needs embodiment, right? It's maybe not just ingesting passive data and doing prediction, maybe there's more to like actually experimenting with the world. So I think that's an interesting hypothesis. We should think about that. And I think another thing that's interesting about robotics is that it's a full stack problem, right? In that it needs you to deal with perception, needs you to deal with dynamics modeling, it needs you to deal with high level and low level planning, control, acting, right? So you need to deal with every different level of the stack. It's not just you do prediction in the void and you're good done. You have to deal with all the different levels. And you can apply learning in different ways at each of the different levels, right? So I think that opens a much richer space of questions for learning than just predicting characters, right? And so I think that's another reason we should study it for intellectual curiosity. Okay, so any other reasons you guys can think of why you guys care about robotics? I think those are the ones I had. Anything wild? No?
It helps us to find out how our human brain works by
Yeah.
experimenting with them.
Right.
We will get to know how it should work.
Yeah. So reverse engineering intelligence. Yeah. Makes sense. Okay. So let's next think about why we care about learning, right? And the argument I find compelling is a somewhat economic argument, which is saying that building for if you're doing a small number of tasks in very constrained environments, you can just build robots or build machines to do them over and over, right? You want to do sewing, you build a sewing machine. You want to heat things up, you build a microwave. But when you want to do a diversity of things where the environment is changing a lot, right? It might be cheaper for you to design a learning algorithm and use domain-specific data than to design a domain-specific machine or domain-specific algorithm, right? So if you want to do any one of these individual tasks, dishwasher is great at washing dishes. You don't need a robot to do that. Or, there's ways to do surgery without having to have a robot do that or having a learning-based robot do that. But if you want to have something that, you can apply cheaply to new environments, that when the diversity of domains is large enough, at some point it becomes cheaper to design a good learning algorithm than it does to design a per domain system. Right? So it's just cheaper. So that's the first argument, I think, why learning makes sense. I think the second argument is that if you want to build generalist agents, when you have learning algorithms, you can have them overfit to the test environment, which makes it easier to do things. Like if I want something in my home, if I have a learning agent that's able to adapt, it can just be really good at my home and not good at anyone else's home. Whereas if I have to just deploy a robot otherwise, it has to be good at all homes, right? So with learning algorithms, you have the ability to overfit to the test environment, which I think will be a lot easier to deploy at some point than just building one agent that works on everything, right? So the ability to adapt is useful that way. So maybe a question we should ask is, should we, drop everything and become AGI nuts? Should we all go work at DeepMind? And I don't think so. I think other people have different opinions. I'm curious to hear yours. So there's a spectrum of, beliefs on this. There's some people who think that, transformer with enough data will solve all the problems and you just need a big enough transformer and enough data. And there's some people who think that we have to design, a state machine or a controller for every different domain. And that has pros and cons. And where I lie is somewhere in between, where you want to have learning algorithms, but you don't want them to just be pixels to torques and give it 10,000 hours of data. You want to bake in some things that make the learning algorithm more efficient or easier or more amenable to real world settings. Right? Yeah. What do you guys think? Does anyone have any opinions on where one should lie here? I'm sure you do. Should we be baking everything in? Should we be, what should we bake in?
Is it a good way of merging like state machines and like learning algorithms?
Yeah.
Pixels to torque.
Right. I think hierarchical RL is one way of doing it. Like you have primitives that you learn, and then you have like a high level planner that maybe puts them together with logic or something like that. So task in motion planning, if you've heard of that, is a good way of merging together these primitives and with some logic and some structure. I think that's one that I find compelling. There's like residual methods which try and like use the state machine as a base, and then they learn residuals on top, which also makes sense. But yeah, I think it's an open area of research. Okay, so there's one article that I thought was interesting. It's called The Bitter Lesson. It's by Sutton, who's pioneer of RL. And he talked about this in like 2018 or 2019. And his argument was that as you bake in more things in the environment, you add more bias, but you reduce variance, right? And he was basically arguing that in every field, like language, computer vision, most intelligence-based fields, we start off with baking lots of stuff in, and then we realize, okay, like that doesn't work, and then we go towards baking less and less and less and less in. Right? So if you look at GPT-3 or you look at like ResNet or like the biggest vision systems, they don't have that much baked in. And so his argument is that for every domain, including reinforcement learning and robotics, we should just bake as little in as possible and focus on the meta algorithms rather than baking structure in. And so he has a cool essay on it. I'll link you guys to it. You should read it. Yeah, so his argument is that nobody should work on, people should just work on getting the right data, getting enough compute, a big enough model. And we shouldn't really work on baking in structure. I think the problem with that argument is that it ignores the cost of data. And it's like, okay, in language, we have a ton of data, but in robotics, the data doesn't exist, and it's not likely to exist unless the robots are already deployed. And for the robots to be deployed, they need to be intelligent. So it's like, it's a little bit circular. So to me, it feels like a little bit of a broken argument because it ignores the cost of data. So I think there's some merit to it, as in we eventually want to go towards things that are less baked in, but to get there, we might need to bake things in to get the right data. But yeah, it's a super interesting article. You should read it. I think it's a good opinion. All right. So, okay. Any questions so far? Any thoughts, comments? Yeah.
Yeah, so for the data side, like I'm really curious about like so in the scale of the data for like robot learning, do you think like how much compared with, for example, language? So right now I think the GPT-3 has like pretty good model, and also it has enough data.
Yeah.
So compared with that side of the data,
Mhm.
do you think is robot learning need more data than that, or like much more, or like less, or like much less?
Good question. I guess it feels like compared to language, we need a lot more data just because the diversity of percepts are much larger. Like the diversity of scenarios that you might encounter are much larger, and the horizon of decision making is often longer. And so it feels like you need exponentially more data just to deal with all the scenarios that you might see in the world. Whereas language is restricted to some set of tokens, right? And so it feels like when you go from the discrete set of tokens to the open world of pixels, like it's much larger. And so that's why I feel like it needs a lot more data. But not the answer. Good question.
It's the structure of the data also matters, and language is kind of structured.
Yeah.
But I think that is
Right.
not as structured.
Not as structured, right. It's not clear how they interpret vision or tactile data. Yeah, I agree. Excellent.
Does data for one robotic system translate to another one well, or does it usually depend?
That's a good question. I think that's an open research area, like cross embodiment transfer, and yeah, we should do a project on it. I think it's great. But right now, it's very much dependent on like one embodiment. So if you have a Franca robot here and a Franca robot there, sometimes we transfer, but not even a lot. But across embodiments is much harder. But it's a great research project. All right. So, okay. So the type of learning that we mostly think about is supervised learning, right? And when we think about supervised learning, we usually think of maximum likelihood, right? So we're saying when you have some X's and Y's, right? So images and labels, or images and segmentations, or languages and language questions and outputs, right? You want to do supervised learning to maximize the likelihood that your model produces the label Y given the input X, right? And so this is what supervised learning is. You usually have a data set T, you sample X and Y from the data set, and you maximize the likelihood under your learned model P hat theta, right? Okay, so this is the thing that we know works, and we want to ask, is robot learning just supervised learning, right? The answer is no, for several reasons. One is because it's a sequential decision-making problem, right? So when I say sequential decision-making problem, I mean, when you take a decision, it affects the next step, which is going to affect the next step, which is going to affect the next step. Each of the steps is affected by your own decisions. And so as opposed to supervised learning, which is IID, right? So you can sample independently and identically distributed from the data set. In robot learning, it's non-IID because every step is dependent on your actions of the previous step, right? So it's fundamentally different there. Practically, robot data is expensive. You can't just collect large amounts of expert robot data the way you do for supervised learning. So the practicalities might be different. You might need a different setup where robot data collection is cheaper. And as compared to prediction, normally in prediction, you're trying to do classification or trying to do segmentation, right? It's like a single task or maybe a few tasks. Robotics is much more multitask and continual, right? So you're trying to not just do one thing, you're trying to fold your clothes and do your laundry and pick things up and put things down and open doors. And the diversity of tasks is much larger, and so you naturally have a multitask and continue learning setup, and so you have to think about those things more carefully. Okay, so seems different from supervised learning. So what are we going to do? Well, we're going to have robots that collect data on their own and use that to improve, right? So we're going to do reinforcement learning. Right? So that's the premise of big part of this class. We're going to cover some other themes as well, but a lot of this class is going to focus on reinforcement learning. And when I say reinforcement learning, I mean learning through trial and error. So interacting with the world, collecting observations and rewards, and then changing your behavior based on those observations and rewards. Right?
Sampling from the policy, but you have to learn from the policy. So it's like, is it like a chicken and the egg question? Or?
So you're sampling from your policy, and then you can try and improve your policy so that when you sample from your new policy, it's better, right? And so you wanna you kind of want to do sampling to figure out which things are good and bad, and then move your policy in that direction. Right? So yeah, it's not quite a supervised learning problem, but you're trying to just infer the parameters so that you're inferring the parameters from the robot's own experience, and you can keep improving. Okay. Cool. So, these are some representations of policies. Okay, so it's a class on deep robotic learning, right? Not just robotic learning. So where do deep things fit in? Is you can represent your policies or other entities like Q functions and value functions that we'll talk about with deep neural networks, right? So you can, for instance, have a policy that takes in your state and produces your action, goes from pixels to torques, or from joint encoders to end effector positions, but you want to maybe represent the whole thing with a deep neural network, right? The idea is you don't have to encode these linear features. You don't have to figure out things for like complex, unstructured environments. You're going to let your deep model do that, right? And so when we say deep reinforcement learning or deep robotic learning, all we're saying is that the function approximators we're going to use for our policies or our Q functions or value functions are just going to be represented as deep neural networks, right? And that doesn't mean they have to be MLPs or ConvNets. They can be different types of models. It just is an umbrella term for all of those, right? And so question might be, is it just pineapple pen? Do we just slap deep models into things and use all of our ideas from robot learning? And as we'll talk about in the class, it's going to lead to some non-trivial challenges when your models are deep, right? Because they're huge and you can't always predict how they're going to behave. So it leads to certain pathologies and behavior, which you have to deal with. And so deep reinforcement learning has a certain set of different behavior than just linear reinforcement learning or tabular reinforcement learning. And that leads to different challenges. Okay. So, natural question to ask is, why should we care about deep RL now? Right? Why is it important now? Well, I think a combination of algorithms, data, and compute have made deep models work super well, right? So we have optimization algorithms that work really well, layer norm, batch norm, SGD, whatever, right? We have tons of data, way more than we had before. And we have massive compute available to everyone, right? Or not everyone, but lots of people. And I think these things are kind of what has made deep learning work super well for lots of other applications. So a natural question to ask is, can we combine the advances in algorithms, data, and compute to do the same thing for robotics, right? So the same way that we had advances in ChatGPT and vision and AlphaGo for games, can we do the same thing for robotics? Because we have the compute and we have the algorithms, and maybe we don't have the data yet, but maybe we can think of ways to get the data. But we want to ask the question: can we leverage these advances and do the same for robotics to kind of get superhuman performance in different environments? So I think that's why it's important now, because deep learning is mature enough in these different environments. It's not quite there for robotics, but I think that's why it's a particularly exciting time for deep RL. Okay, so a natural thing to think about is, where has RL been successful? So it's been successful in, board games, in simulated environments. There's some stuff on balloon navigation in gusty environments, chip placement, training some of these language models, right? Traffic management, video games like StarCraft or Dota, right? So those are some environments that RL has been pretty successful in. Are there other ones that people think about? These are the ones that I could think of where it has actually mattered. Any other ones that I missed?
Yeah.
So model based is one of that.
Yeah, right.
They did some really awesome work at Robotic where they learned the dynamics model from the vehicle
Right.
from data. Then they would just like
Mhm.
model based reinforcement learning to figure out the best possible route.
For like the rally car stuff.
Yeah,
you
yeah,
think?
yeah.
Right. Yeah. So off-road autonomy.
Yeah.
Yeah. It's a good point. Yeah. Yeah. So a little bit of robotics, but I would say that RL hasn't really made, or deep RL hasn't really worked in robotics at scale yet. It's starting to. But these are examples where, these kinds of things are like at production level, right? Or you're like playing against the world's best Go players, or you're solving, games to superhuman levels. You're deploying traffic solutions, and robotics isn't quite there yet, right? So, but all of these domains are, simulated, or a lot of them are simulated. You can collect data somewhat easily. Rewards are somewhat easy to provide, right? And I think in those kinds of domains, RL has been really successful, right? But it's not always the right call, right? So I don't think it's particularly good in domains which are very safety critical, right? So you're learning through trial and error. It's not like if you're trying to like fly a rocket and it's like got people on board, don't do deep RL. Not a good idea. Or you're trying to do something that's repetitive, right? So you have a factory, the same thing's happening over and over again. Don't do deep RL. It's not a good idea. Do motion planning and it'll just work way better. Or if you're trying to do surgery, I don't want to, do trial and error inside somebody's body. And so I think these kinds of applications, there's better choices than deep RL or even deep learning in general, right? So I think you want to think carefully about which domains are amenable to these methods and which domains are not. Right? Like some of the insights might transfer, but in general, I think safety critical or repetitive domains are not the right ones. I don't know. Yeah. I think I grabbed it from like an aircraft navigation paper. Right. So what we're going to focus on in this class is where domains where RL is potentially useful. It has the potential to be useful, but it hasn't really worked out yet for some reason. So what I'm thinking of is like robotics in unstructured environments like the home or outdoor navigation or things like that, where data collection is not horribly risky. It's not going to kill anyone immediately. You're not going to crash a rocket. But there are some challenges in data collection, which has made it non-trivial to apply. But the diversity of the environment is large enough that it warrants reinforcement learning. Right? If you want to deploy in every different home, you want to have an algorithm that gets better, is adaptive. You have all the benefits of reinforcement learning that you want, but it's not so dangerous or so repetitive that RL is not a good idea. Right? So those are the types of environments we're going to focus on. Yeah.
So the idea with the environment having to have high diversity is otherwise you just bake in some algorithm.
Yeah, exactly. So it's like if you want to, make pizzas, like I don't think RL is a good idea. Okay, so when we think about RL and robotics, we want to use them in these unstructured environments, right? So environments which have high amounts of diversity, variability, and complexity, right? So things like manipulation in a kitchen or in a home, or like navigation in a complex office building or on some unstructured terrain outside, right? And so we want domains which have these properties, and you want continual improvement in the real world. So you want to do reinforcement learning in the real world. And those are the kinds of domains that you might see benefits in, right? So home robotics, outdoor navigation, in some cases, drone navigation in unstructured, wind environments or, lighting conditions and so on, right? So I think those are the types of environments you want to think about. So putting your roboticist hat on, those are the types of problems we're going to think about in this class. Right? We're not going to think about industrial plugins. Okay, so when we think about a typical robotics pipeline, right, it's going to start with perception. They're going to do some sort of state estimation, filtering, right? You're going to then do some amount of modeling. Usually you have a simulator or a good plant model, right? You're going to do some amount of low-level planning, like motion planning, some amount of high-level planning, which is like which tasks should you put together, like a state machine you were suggesting, right? And then you're going to try and put those together, give you a plan, going to execute your plan with some low-level controller with PID or something else, right? And that's going to give you your robotic system. And like most robotic pipelines, which work well, kind of work like this, right? Some variant of this. But what we're going to do is we're going to kind of throw all of that away. And we're going to say we want to do perception to action, right? Or some version of that. And we're going to represent the whole thing with the deep neural network. And you're going to try and learn this neural network with experience, right? So you can see that we're removing some amount of structure, but it's not as simple as, pixels to torques necessarily. You still need to choose which parts of the interface you learn. Basically, the interface from perception to action is variable. You can choose what your perception is, and you can choose what your action is. And so there's still decisions you need to make on where to draw the line here. We're not always going to go from, draw pixel values to currents on your robot arm. So there's still decisions to be made there, but we're going to try and do a lot more end-to-end learning than a traditional pipeline. Right? All right. So why should we do this? Does anyone have thoughts? Why would we want to do something that's end-to-end?
Might make developing faster if it actually works.
Right. Developing faster, right? Other thoughts?
I just have
Yeah. Maybe you were
your environment's like hard to model.
hard to model, right?
You can't model it.
Yeah. That makes sense. Yeah, go ahead, sure.
I just have one question about
Yeah.
like, so, I guess maybe this is not yet what you do in practice, because at the deeper on you're all still in the field. What we like talked about earlier, which is like you kind of want to be on that spectrum of being like, baking in some items, but then not like fully learning everything. You're learning from scratch.
Yeah.
In practice, like going back to the previous slide, do you do somewhere like in between, or do you shift between like that 12 version to the low one?
Yeah. In practice, sometimes you like use some state estimation method and then you learn things on top. So that's what I mean by you can like shift how much you're end to end. And so you want to, subsume some part of the pipeline, but not the whole pipeline. I guess the most extreme version is the whole pipeline, and then you like vary what you learn.
Is it like some kind of abstraction or something?
Yeah, you could just define the abstraction depending on your problem, basically. Yeah, exactly. That's a good way to put it. Okay, so some things that I thought of was that, when you have an end-to-end system, like the modules compensate for each other. If you have a state estimation issue, your next module can compensate for it. Whereas if you had independent systems, they don't really compensate for each other. In some problems, you don't even know what the interfaces should be. In some problems, you don't even know what the pose in a symmetric object, you don't know what the pose should be. And so you can avoid hand designing these interfaces in problems where it's not clear. And lastly, it just works better sometimes, right? Because of those reasons. But you have a lack of interpretability. You don't know what's happening in a big, deep model. Often you have a lack of reusability. So if you have, a state estimation module, you can use it for many different planning modules. But if you just have an end-to-end system, sometimes it's not reusable. And there's, an active area of research on how to get the benefits of end-to-end while being reusable. And often it just requires a shit ton of data, right? Because you're trying to look at every single possibility of everything that you might encounter, which might take a lot of data, right? So there's pros and cons. But we're going to look at largely end-to-end systems or things that are close to end. Right? Okay, so a natural thing to ask is, okay, we seem to know a lot about it. Why haven't we solved it yet, right? And there's this nice conjecture that this guy Hans Moravich, proposed a couple of years ago, which is called Moravich's paradox, which says that it's relatively easy to learn high-level reasoning things like games or chess or so on, as compared to low-level skills, right? So things that you think are complicated, like reasoning, are often really easy, and things that you think are easy, like motor control or walking or things like that, are actually really hard. And the evidence that they provide is, okay, like in evolution, it took billions of years to get to something that can walk, and it just took a few million years to get to things that could reason. And so it's a bit of a heuristic argument, but so far it's kind of proven true. We're getting great things with the GPT. It's reasoning, it's answering questions, but robotics is barely walking, right? And so it's not because we haven't tried. I think it's because it's harder. right? But that's vague and it doesn't give us anything. So let's think about more concrete reasons, right? And I think the concrete reasons come because of a mismatched set of assumptions between what most of these algorithms assume and what we have in the real world, right? So let's look at a domain where these RL algorithms work. So something like an Atari game, right? You see that rewards are easily available. You can collect free amounts of data. You can control the game state arbitrarily, right? Whereas a robot in an environment, what is the reward? Nobody's telling you the reward, right? Or the amount of experience is finite because robot experience is expensive. You can't just magically teleport the world to any state that you want, right? So you don't have magical control over the world. And so there's this set of mismatched assumptions between domains where these things work, like things like Atari games, and domains where it's been more challenging, like real world robotics, right? And I think that these mismatched assumptions is kind of what makes it hard to apply reinforcement learning to robotics and why we haven't just solved all the problems. Right. So these mismatched assumptions really boil down to the fact that data-driven systems need the right data, and if you don't have the right quality and quantity of data, you can't really learn, right? And so in reinforcement learning, what you have as data is state, action, next state, reward tuples. Let's say they're S, A, R, S prime. You have n of them, right? And you're sampling them from some distribution P, which is changing as your policy gets better, right? And so you need to make sure that you have the right rewards, the right supervision R. You get data from the right distribution, so your policies are exploring the right way to get the right data P, and that you're able to get enough data or get enough signal N, right, in order to learn things, right? And so I think to get data-driven systems to actually work, we need to make sure we have the right supervision, the right distributions, and the right amount of data through these three factors, right? And so I think that's really what this class is going to center around, is how do we make sure that these reinforcement learning algorithms for robotics get the right type and quantity of data. Does that make sense? And we're going to try and put those things together to build robotic systems that work on real-world problems. So a natural question to ask is, maybe you don't have time. Let's skip this one. Okay, so what we're going to focus on is three different ingredients, right? So we're going to have algorithms, we're going to have supervision, and we're going to have efficient transfer, right? So the first part of the class is going to focus on RL algorithms that are performant, can work in the real world, are data efficient, stable, so on, right? The next part of the class is going to focus on how do we actually supervise these algorithms, how do we provide them reward, how do we provide them guidance from humans, from videos, from data sets, so on. And the last part of the class is going to focus on how do we make this whole process efficient enough to run in most settings. So how do we get transfer from other tasks, other robots, prior data sets, simulation, and so on to make this whole system practical enough to run in the real world, right? So we're going to kind of divide our class into three different subparts, and each of the subparts is going to focus on one of these three, right? Okay, any questions? Okay, so first question to ask is, what does supervision look like for robotics, right? So what we want to do is we want to infer rewards from raw sensory perception, right? So you have a camera looking at a kitchen. You want to be able to figure out, okay, I tried to put the kettle in the sink. How good or bad did I do, right? And so in a video game, you have your score. In a kitchen, you don't have your score. And so a lot of the methods we're going to focus on is how do we take raw perception and how do we figure out how to supervise these algorithms from raw perception, raw sensory input, right? And so this is quite difficult. It's not quite solved. So lots of open research questions there, right? And so, people try to do supervision from human demos. So they try to have some people demonstrate how to do things like play ping pong, use those to infer reward functions that you can use to learn in the future. People try to do things with intrinsic supervision. So they try to do things where you have robots assign themselves rewards through curiosity or novelty or self-supervision of sorts, right? And use that in order to learn. And you have things like learning from videos or images or large pre-existing data sets, right? So you can have people demonstrating videos or large existing data sets, use those to infer reward functions and try to use those for supervision. Right? So lots of open questions, but we're going to try and look at some set of these. The next question we want to ask is, what do good RL algorithms look like for robotics, right? So for simulated environments, you can have algorithms that do crazy stuff, right? So if you look at the thing on the bottom, the humanoid is falling down all the time. You take a $100,000 robot and you do that kind of stuff with it, it's done in a week, right? And so real world data on robots is not free. You have to think about efficiency. You have to think about safety. You have to think about where this data comes from, how much of it you have, right? And so we need to we need to develop algorithms that care about data efficiency, that care about safety, that care about these kinds of things. And so it's not as simple as just designing an algorithm that gets as high a reward as possible. You have to think about the other constraints in the problem. Right? And so what we're going to study is, a class of algorithms which are on policy, right? So things that are using their latest set of experience, which are simple, high performant, but quite data efficient. That's how we're going to start. Then we'll go to off policy algorithms, which are a little more complicated, but often a lot more data efficient, but sometimes unstable. And we're then going to go to model-based RL algorithms, which try to, as Chuning was saying, learn a model of the world, right? And these are a lot more data efficient in many cases, but they're challenging to scale to very difficult tasks or long horizons, right? We're going to think about what combinations of these methods give us what we want and what the pros and cons are of each of these, right? And lastly, we're going to think about, when you take our RL algorithms, it's often too slow to run them from scratch for every task. So how can we use priors, data, computation from other sources to make this a lot more efficient, right? So can we use priors from simulation? Can we use priors from other tasks, from other robots, and hand-baked in priors from humans, right? How do we use transfer from other sources in order to make this whole process efficient? So this could consist of, multitask and meta reinforcement learning, which is trying to say, okay, you've solved K tasks and you're reaching the K+1th task. How do you use the data from the K task to help the K+1th task? Right? And so we might want to consider, a whole set of tasks. You've learned 45 of them. You're going to the last 45 to 50. What do you transfer from pushing the door unlock? What do you transfer from window opening to hand inserting or so, right? So that's one of the paradigms we're going to think about. We're also going to think about this paradigm of offline reinforcement learning, which is saying that when you have large pre-existing data sets that, let's say, you've collected through experience or experts have provided to you, or they're provided through researchers who spend a long time collecting these data sets, how do you effectively leverage them to bootstrap your algorithms? And then we're going to think about if we had simulations, let's say they're approximate or in a few scenarios, how do you use them to bootstrap learning in the real world? So how do you do simulation to reality transfer, right? And how do we make that scalable to general problems and so on? Okay, and so to kind of sum up the landscape of things we're going to think about algorithms, we're going to think about supervision, we're going to think about efficient transfer, right? And so by the end of the lecture, hopefully we'll color in all the white rectangles, and we should have a better understanding of what are the components to design, good robotic learning system. Okay, so just zooming out the last 2 minutes, I think we talked a little bit about, intelligence needs embodiment. And so beyond robotics, we want to think about intelligent systems, right? And the hypothesis is that elephants don't play chess. And so there's a nice article by Rodney Brooks called Elephants Don't Play Chess, which argues why we need to think about studying intelligence in interesting, complex environments, right? And so the thought is that we want to go from really, really simple simulated environments to slightly more complicated environments in the real world, to really, really complicated environments in the real world with humans interacting. And the types of behavior we're going to get are going to become increasingly interesting as we go from simple to more complex environments, right? And so hopefully through the class, we'll try and figure out how to go from these really simple environments to really complex ones and see what the change in behavior is. That's it. This is Shaky from the 50s. Yeah, that's it. Thank you. Yeah. You want to ask questions, stay back. Happy to talk to them. And one thing before you all leave is we will post some readings. Kay has already posted the readings. Just read any one of those papers. They're all amazing. And post some thoughts on STEM. And we'll start at 10. You guys can just post thoughts. And we'll see you on Monday.